Good day, Mr. Tan.
Hi, good evening, good day. Eve, I guess.
Yes, sir.
Okay. Yeah, good afternoon, good afternoon. Yeah, we have 100 plus already now. Okay, so I unlock the attendance first, yeah. Okay, please sign in your attendance, yeah. Please sign in your attendance. Your attendance is very important. Yeah. So, well, before we start the class, okay, I would like to find out a little bit about your password on the Smart Science. Is everyone already obtained your password?
Yes, sir.
Yes, sir.
Yes, sir.
Already, sir.
Okay,
Got
good.
it, sir.
Okay, good. Thanks. All right. So I will post the informations and requirement later. Okay, right. So you don't do any experiment first at the moment. Okay, you can just if you are in, okay, you accidentally go in already. So just don't do anything yet. All right. Okay, just go and view. Of course, if you already follow the instruction, you already started actually, all right? Because the instruction is quite clear, right? They just say, okay, you have to go here, you have to push this, you have to view this, and so on, all right? So anyway, try not to answer any first, okay? Because I will not ask to do as many as what you see. Probably you have seen all the labs that it posted there, but actually it shouldn't be like that, okay? It should be something that we actually assign to you, okay? But I'm not sure why it's already posted out everything there, okay? Right, so that's why you're probably not sure which one is for the just exercise or fun, which one is for the evaluations, right, for assessment. So just don't, if possible, don't go and do anything yet, okay? Probably you just can view outside. Of course, if you started, okay, you go in, then of course it will immediately started all the evaluations already, right? Okay, good. That you all already obtained the password, okay? It's just that the system technically is not that right, okay? You only should be able to view something that we assign, but now everything is there, okay? I have not yet assigned, but it's already there, everything. So I'm not sure what's right, what's wrong, okay? Anyway, just want to know whether you have gotten the password. Okay, all right. So we have completed. Okay, so we have completed the first two lessons. All right. So I hope you all have tried the example, those in the notes again, and then as well as the tutorial. Okay, so as I say, I will post the additional exercises. Okay, I think I already posted one of the additional exercise. Okay, so I will post it another one hopefully after the lesson, right? So of course there's quiz, which actually is not really have a good response. Okay, not many is trying the quizzes. Okay, but I'm sure those who already tried, that is good. Okay. So let us continue today's lesson. All right. So today we are going to look at the third lesson. Okay, we are going to look at the third lesson. So of course, this is going to be the combinations already of what we have learned from the first lesson and the second lesson, right? So first thing is we need to know what is the quantity, what is the units, right? And then what is the scalar vectors quantity. So today we're able to slowly learning the motions of an object, all right? So today we just look at the motion, okay? Just that, okay? How this object move, going like this, like that, and so on, just that, okay? So today it's just about how the object moves, all right? Okay, so the objective of what we are going to look at today, generally we are looking at two-dimensional motions object, okay? So of course we are looking at the displacement, velocity, accelerations. After that we are going to actually derive, okay, we are going to derive the quantities of this speed, the velocity, and the accelerations, all right? What is the relations between this quantity, right, and the displacement? After that, we are going to look at, okay, a specific case of the constant accelerations. Okay, so we are going to look at what is the constant accelerations, all right? So how the object is moving when it has constant accelerations. And from this, okay, we have a specific cases, which is the free falling body, okay, which means a free fall, all right? So we are on the earth, so we have the accelerations of gravity, right? So that is a constant accelerations. And the final part is going to be two-dimensional motion. That is going to be the projectile motions, okay, projectile motion. So this is what we are going to learn in this lesson 3, okay? Of course, we are not going to complete this today, all right? It is quite a lot, okay, especially the projectile motions as well, okay? It's quite a lot. So hopefully we will be able to reach constant acceleration at least, okay? So we'll see how is it goes, doesn't matter, okay? So we just go as it is, okay? Whether it's fast or not, it depends on our speed, okay? Right. So first thing that we need to know when we are now trying to find how we move, of course, we need to find out the meaning of the distance and displacement. Anyone know what is the difference between distance and displacement? Yeah?
Distance is scalar and then displacement is vector.
Great, excellent. Okay, so distance is a scalar, displacement is a vector. So distance means any path, any step, okay? Any movement that we step on the floor, on the ground, or any object that actually move in any kind of path, so that path is considered the whole journey, the whole length of that object, okay? So it will actually calculated every path, okay? So that is going to be the distance taken. So it's not about the directions at all, okay? It's not involving directions at all. Any path taken by this object, that is the distance taken, okay? So that's how we refer to the distance. And how about displacement? We say it is a vector quantity. So it is actually a distance that is measured from these 2 points that we are from to the final point, okay? So we measure these 2 points in a straight line, which means we are connecting these 2 lines in the straight line, okay? So we are measuring the shortest distance between these 2 points, all right? Okay, so okay, let me change my pointer first. Okay. All right. So we are actually measuring the distance from these 2 points. Okay, right? So this is the starting and this is the end. So we are measuring a straight line. Okay, a straight line from the initial point to the final point. And of course, the distance is there. Okay, that is measured length. So that is the distance. How about the angle? Okay, of course, if we refers to the certain directions, if this is x-axis or if we consider this as the east, right, then we can measure the direction. All right, we can measure the direction. So therefore, the displacement is the length, which is the shortest possible length measured from the initial to the final point. All right, and the direction, of course, is from some reference axis, okay, or direction. Okay, so if we want to actually conclude these two, distance and displacement, we can just take these 2 points, all right, a starting point and the end point. So if we say about distance, okay, it can be any path, okay, any step taken, if not about the directions, okay, it can be any directions as long as it step on the ground, that is considered the distance taken. And the displacement, it means the length measured from the starting to the end. All right, sorry. Okay, so we have the shortest distance measured from the start to the end. All right, so that is the displacement. All right, so everybody, I believe, already understood how we can actually differentiate between distance and displacement. So this is the fundamental, the basic. If anyone asks us, okay, so I hope you already able to clearly tell them, okay, in a layman word, okay, what is distance, what is displacement, okay. All right, so next we will like to look at this position of the object. All right, the positions of the object. So every time when we want to actually measure one object position, okay, when we say position, then of course we are looking at the directions as well as the distance. Okay, all right, so therefore we know exactly the positions of the object. All right, the positions of the object. So let us look at this axis. Okay, we just consider this one direction, okay, one dimensional. So we have consider the x-axis. Okay, so when we want to know what is the positions of the object, first thing is we need to know where is our reference point. All right, where is our reference point? So we need to know our reference point first. Where is our reference point? All right, so now we need to consider our reference point as the origin. Okay, that is what we commonly consider. We always consider our reference of the origin, okay, as the 0 axis coordinate. Okay, all right, and then okay, and then only we look at the direction. If the object is on our right, which is on the positive x-axis, so that means that is going to be a positive, okay, it's positive displacement or positive positions, okay, from the origin. All right, and if the object is on the left, then we of course need to mention or indicate the negative there, so that we will be able to know that this object is actually on our left instead of on the right. Okay, all right, so that is very direct. We know exactly if it is on just one dimension, it's very direct, very simple. If it is on our right, it is a positive value. If it is on the left, it will be the negative value. Okay, and of course the magnitude is the length. Okay, right, from where we are, the origin to the point of the object. Okay, all right. I hope you all got it. Okay, understand that? Any questions until here?
No, sir.
Oh, good, sir.
Okay, good. All right. So that is the position. All right, that is the position. Then, if you would like to find the displacement, okay, the displacement, we just need to find the difference of these positions vector, or we can actually take a vector of the displacement also. Okay, anyone. Okay, so it depends on how we want to actually solve and find our displacement. We can also take a position vector, or we can also take the displacement vector itself. Okay, so for example, if we have the positions of the object, right, somewhere at the origin, okay, so we have the object move at certain point, okay, so this is its first displacement. And from there, it actually move again, then it has second displacement, right or not? Okay, so we can actually find the total displacement is by taking x1 plus x2. Or maybe after that, okay, let's say after it reached this point, it moved back to certain point, which is x3, right? So this is the negative displacement, of course, right? But if you want to know what is the total displacement, we still add up x1 plus x2 plus x3 displacement. It's just that x1 and x2 is a positive displacement, but then x3 is going to be a negative displacement. Okay, all right. Of course, we will meet with a few of these examples later as well. All right. Okay, so that's how we actually find out the displacement of the object. All right, displacement of the object. All right, so let us look at the first example. Okay, let us look at the first example. All right, so here we have an object. Okay, of course, it gives us a certain position already, right? So this object is moving from point x1 at time t1. Okay, from the point x1, the time t1, and then to the point x2 at the time t2. All right, so x1 at t1, x2 at t2. But of course, they gave us two possibilities here, all right, A and B, right? So the first one, they tell us if x1 is 20 meters, okay, if x1 is 20 meters and x2 is 50 meters, that is the position, okay? That's why it says at the point, okay? That's why it says at the points, right? So that is the position, right now. So the object, okay, the object for the first one, it says, right? So the object initially at 20 meters and then later on at 50 meters. That is the position of the object, okay, all right? So if we want to know what is the displacement of the object, okay, what is the displacement of the object, then of course we are actually taking the difference of these positions, all right? So we actually have the initial is 50 minus, okay, the final is 50 minus the initial, which is 20 meters, okay? So of course we will actually obtain 30 meters, and this is positive, so exactly we know it is in the positive x direction, okay? So for the first condition, okay, for the first condition we have, okay, for the first condition we have the object actually from 20 meters, right? So it moves to 50 meters. So as you can see, this vector here, right, the displacement is positive, right? The displacement here is positive, right? The displacement is positive. So it is in the positive x direction, okay? Right? Exactly from the answer, we know it is in the positive x direction. And then we look at the second condition, second condition is say it is actually initially at 50 meters instead of at 20 at the beginning just now, right? But now it is actually at 50. Okay, it is now at 50, and at the end it goes to 20. All right, so it is from 50, it moved to 20. All right, so it's very clear. If we draw, we can see exactly the diagram, from the diagram, how the displacement takes place right now. So if you want to write it, okay, so it will look like this as well, because x2 is still x2, all right, the final minus the initial, all right. So x2 now is 20, all right, and x initial is 50, all right. So we have 20 minus 50, so we get minus 30 right now. So it shows clearly that this object is actually moved to the left side, all right. Okay, so one dimension is very clear. When it's negative, you know exactly it is moving to the left, and then the magnitude shows how far it is displaced. Okay, so in another word, we can also add the information. If you want to, we can say it is moving in the negative x direction. Okay, all right. Okay, understand? Any questions for this example one? Yeah?
No question, sir.
Okay, good. Very clear, yeah? Okay, good. We look at second example then. Okay, so this second example, okay, of course, okay, I want to actually explain a little bit here. Although you can see that the curve that made at A here, all right, the curve that made at A here is so large, okay, but the actual displacement is just actually something like this. So the athlete actually moved to A, and then from A it make a turn to B, just like that, something like that. It's just a point, all right, just a point, from point to points, right, just from point to point, all right. Okay, so this athlete runs 6 kilometers due east. Okay, so we know exactly already it is taking the right directions as east, okay, and then it make a U-turn back to travel a distance of 2 kilometers, okay, 2 kilometers, and then what we are asked is to find the distance covered as well as displacement, okay, all right. So what is the distance? How you actually find the distance here? How you get the distance?
6 plus 2.
Yes, it's very direct, correct. Okay, because that is the path taken. So we just add up any path taken by the object, here the athletes. Okay, so we just add up all the path taken, so that will be the distance for the athletes. Okay, how about displacement? How about displacement?
6 minus 2.
Okay, very good. Okay, very good. So we have the first displacement. Okay, x1 is positive right now. So the object, the athletes actually make the first displacement right now. So the athlete make the first displacement, and then it make the second displacement. Okay, so it make the first displacement to the right, the second displacement to the left. So what we have, of course, the first displacement is a positive, right? And the second displacement is a negative. Okay, all right. So we have 6 minus 2, that is 4 kilometers. So it's very, very obvious the displacement, right? This is the displacement of the object, all right, of these athletes. It is going to be 4 kilometers. Okay, and of course it actually mentioned just now east, So of course, this athlete actually has a displacement in the east direction. Okay, it has the directions towards the east. Okay, all right, very good. Okay, very good. Then we move slightly to the 2-dimension. Okay, 2-dimension. Okay, so we look at the third example. Okay, look at the third example. So this vehicle traveled 3 kilometers east, okay, and then 3 kilometers north. Okay, so it's very clearly shows by the diagram. Okay, so if we want to get the axis, we know this is the direction it actually indicate the east, right, and the north. Okay, the east and the north. Okay, all right. So what is the distance and displacement? So how do you find the distance here?
3 plus 3.
Yes, very good. Okay, very direct, this one. The distance is just 3 plus 3. Okay, so since we already learned about the scalar and vector, I'm sure you're already familiar with this. Okay, then how to find the displacement? You must be familiar with this.
Pythagoras.
Yes, we use the Pythagoras. Okay, we use the Pythagoras. So we have 3 square plus 3 square, and then we take the square root. Okay, so we have the magnitude of the displacement. Okay, how about to get the direction? How do we get the direction?
Tangent theta.
Yeah, which is your theta?
BOA. Angle of BOA.
Okay, right. So you can take this as the angle, right? So normally we try to take the angle with reference to the point from where it started, right? Why this pen become like this? Okay, so that is the angle, all right? Okay, so actually, okay, I don't mind if you all just indicate this angle and then find the angle. What happened? Let me change the pointer. Okay, so we have theta, yeah. So arctangent of 3 over 3. So I need to write very slow. You cannot detect. Okay, so from here, of course, it is equivalent to 45 degrees. All right, 45 degrees. Okay, all right, so that is sufficient. All right, the direction is 45 degrees north of east. Okay, all right, so that is how we actually obtain if it is for 2 dimension. Of course, here is very simple example for you. All right, so any question for the distance and displacement? Anyone want to ask about the directions or anything? No, yeah?
All good, sir.
Okay, thank you. Okay.
No questions, sir.
Okay, thanks. All right, we go to the next quantities. Okay, next variables. Okay, all right, we go to the next variable. So we have average speed. Okay, so of course, generally when we say speed, that is actually represent the average speed already. Okay, when we say the speed, that is the average speed of the object already. So speed, as we know, is just a scalar. All right, so it is measured, okay, or calculated as a total distance over total time. All right. So this is a very general definition for this speed quantity. Everybody, I believe, know about this quantity very, very well. All right. So if we already know about this quantity, right? So let us look at the example then. All right. Let us look at the example because it's just about speed. So it's just about quantities, right? Just about the speed, the distance, the time. So let us look at the example. Okay, the first example. Okay, we have a cyclist. Okay, we have a cyclist here. So the cyclist travel in 90 minutes along a road. Okay, as it says here, a straight road. Okay, then its average speed is 16 kilometers per hour. Then the question wants us to find out how far actually this cyclist has traveled. Well, of course, the answer is there. So how do we do it? What should we do first?
First of all, we convert the 90 minutes to 1.5 hour.
Okay, then?
And then we multiply by 16 kilometer per hour, then we will get 24 kilometer.
Okay, very good. Okay, so you can actually do that, all right, to find the distance as we already defined just now. Okay, the average speed is actually given by what quantity? Distance over time. Right on. Average speed is given by the distance over time. All right. So if you want to find the distance, that is just equivalence to the speed times time. Okay, so as what your friend suggests, yeah, that's very good to find the time first in terms of hours, because as you can see here, they gave us in minutes, right? They gave us in minutes. They gave us 90 minutes, correct or not? They gave us 90 minutes. So we need to actually find in terms of hours, then only we can multiply with this speed that we have here, right? If not, we will not be able to multiply, okay? Minutes with hours, we cannot multiply that, okay? It is not same unit, okay? So therefore, we should actually convert the minutes to hours. You can actually show it in a single calculation to find hours, or you can just calculate it together. It's fine, okay? Because the questions here want us to find the distance only, all right? So you can actually calculate personally individually by finding the hours, or we can immediately substitute by calculating in a bracket. All right, so we can write it in this way here, right? We can just write 16, okay, kilometers per hour. Happen. Okay, 16 kilometers per hour. All right, and then times the time, which is hours. So it is 90 minutes. Divided by 60 minutes in 1 hour. So we convert the minutes to hours. So we have 1.5 hours, just like your friends mentioned. Okay, so we get the distance is 24 kilometers. Okay, 24 kilometers. All right, okay, good, very good. And then we look at the second example. Okay, something quite similar. Okay, something quite similar. Let us look at the second example. So we have this Earth orbiting the Sun. Okay, so this is a very common quantity that we are going to met later on. Okay, until the next semester also, we are going to see this quantity here, the average distance between the Earth and the Sun, 150 million kilometers. Okay, then it asks us, how long does it take for the light from the Sun to reach the Earth? So how do we do this? So this is roughly how we actually always saw the photo, okay, the sun with the orbiting Earth, all right, okay. So how long does this sunlight, as it released at a point of the sun, to actually reach the Earth? How long does it take? Okay, how long does it take? So how do we do it? Yeah.
First you convert 150 million kilometer to meter.
Okay, very good. Then
Then you divide it with the speed of light.
great, excellent. All right. So we first try to get this distance, the actual distance. All right, the actual distance between the sun and the Earth. Okay, so 150 millions. Okay, 1 million is 10 power of
6.
Yes, that's right. This computers is what happened? 10 power of 6. Okay, 10 power of 6. And then kilometers is
10 power of 3.
yes, 10 power of 3. Okay, 10 power of 3. Okay, good. So we can rearrange this. Okay, so we have 6 plus 3 is 9, and then we can move this decimal place to between 1 and 5. So we will get 1.5 times 10 power of 11.
9.
Correct?
Oh,
yeah. Okay, good. So we now would like to find the time. Okay, so the time is just the distance over the speed, as your friends mentioned just now. So we have 1.5 times 10 power of 11 over the speed of light. So we will obtain the times in second, of course, in second, although I give in minutes, right? Okay, so the time here is in second because it's meters per second. Okay, right? But the number is a little bit large sometimes to have some sense of daily sense, right? Or common daylight. Okay, so if people say second, 500 seconds, we can't really imagine that how long is that. So we change it to the closest unit, that is minute. So we just multiply this quantity, right, with a constant, okay, a factor, conversion factor. So we have 1 minute okay, 1 minute is 60 seconds. All right, okay. It's so slow a bit today. All right, so that is it. Okay, is it correct? 8.33 minutes.
yes,
yeah?
sir.
Okay, good. Around obtain, yeah.
Shouldn't the final answer be given in the SI units?
Oh, it doesn't matter unless the questions mention. Please give the answer in SI unit. Okay, as I mentioned just now, if you stop at 500 seconds, it's fine. Of course, I didn't say it is wrong. Okay, it's just that we want to know some quantity, which probably it's just like a days, right? If someone tell you, okay, it is 340 days. So maybe you want to know, 340 days, how long is that? So if we change a year, so roughly we know, oh, okay, it's a year plus, okay, a few days. Then we will know roughly how to actually compare it in the common quantity, right? So it doesn't matter. It is all right if you want to give in 500 seconds. All right, it's all right. Okay, can ya understand? Is it okay?
Yes, sir.
Okay, good. All right, so that is a common example of distance and then with speed. And then, of course, the next one that we are going to look at is the most frequent that we are going to meet is the velocity. Oops, sorry. So the average velocity, all right, the average velocity. So we know that average velocity is a vector quantities, all right? Average velocity is a vector quantities, okay? So what we have is displacement over time, all right? Displacement over time. Okay, so what we have is still the same, okay? A vector, a displacement, right? So this is the displacement here, all right? Okay, displacement divided by time, all right? Displacement divided by time. So we have a vector quantities as well, which is as a unit of meters per second, okay? Meters per second. So I hope you can hear my voice clearly.
Yes, we can hear you, sir.
Oh, okay, good. All right. Yeah, because the line is a little bit bad today, right? Okay. Okay, good. Then we move on to some explanation further on this average velocity. So this is roughly the diagram that I have taken from a reference. Okay. So the functions given is the green line that shows here, okay, on the graph here, right? So this is the displacement function, right? This is the displacement function, right? So the object actually moved, okay, from the from the time zero, okay, not from rest, it's from time zero, and then it moved until the time is 4 seconds and further, of course. As we can see, the graph is still going further from 4 seconds, but we just record here is from 0 to 4 seconds, all right? So the path taken, as you can see, is a curve, all right? The position, every moment, every 0.01 second is measured, okay? So that's how the path can be recorded, okay? So the average velocity that we want to find, we need to actually connect, okay, by graph, we need to connect these 2 points. We want to measure what is the average velocity between the time interval of 1 second to 4 seconds. All right, from 1 second to 4 seconds, what is the average velocity? So as you can see, we draw a line, a straight line between the time of 1 second to 4 seconds. It is not the actual path, you see, right? So the actual path is the actual movement. But when we take average velocity, okay, when we take the average quantity, it is not going to show the actual motions anymore. Along the 1 second to 4 seconds, the path that we move now is along the red line, all right? Because we are taking the average. So to take this average, of course, we have 2 meters, okay, as you can see, all right? As the object reach 4 seconds, the time interval from 1 to 4, right? So it reach 4 seconds, the position is at 2 meters, right? The position is at 2 meters. And when it is at 1 second earlier, it is at -4 meters. Okay, that is the position. So therefore, what we have here will be 2 minus of the initial, which is -4, divided by the time difference, 4 minus 1, then we obtain 6/3. So it is 2 meters per second. So here we know that this object actually is moving towards the positive x directions. All right, the positive x direction with 2 meters per second. Okay, all right. So that is roughly when we are considering the average quantity. We are not getting the real motion, but we are getting the average already. Okay, so anything that is the real motion, we are not going to know what is actually happened. Okay, because now our motion from the 1st second to the 4th second is along the red line. Okay, around the red line. Okay, let us look at the first example. Okay, the real example just now is how we look at the average. Okay, so now if you look at the first example, okay, we have this position of a runner. Okay, a position of a runner they gave us during this 5-second interval is at x1, which is 80 meters, to x2, which is 50.5 meters. So what is the runner's average velocity? Okay, of course, we already learned just now, okay, how to find the average velocity, which is the final minus the initial divided by time. Okay, so that is very, very direct. Okay, so we have the final is 50.5 minus 80 divided by 5 seconds. So it's very direct. We obtain minus 5.9 meter per second. So from this answer again, okay, from this average velocity that we calculate, we know exactly that this runner from a reference point, the origin, we know that it is actually running to the left of the origin at a speed of 5.9 meters per second. All right, okay, understand? I hope you got it. Any question for the average velocity?
All good,
No
sir.
question, sir.
Okay, good. All right, very good. So next, we would like to look at the actual velocity. This is only average, as what we say just now. Ayo, we lost the information here and there. Now, next, we are going to look at the real velocity, which we call it as the instantaneous velocity. Okay, instantaneous velocity. What does that mean? It means we want to get the velocity at that instant. How do we do that? We just make sure the time difference that we are measuring just now as small as possible. Okay, as you can see here, this is how it defines the instantaneous velocity, right? So they take the time difference as close as possible to 0. All right, the time difference that we measure just now close as possible to 0. So when the time difference is close possible to 0, then we will get exactly at that particular instant. For example, if you want to find at 1 second, right? So we try to bring just now the time at 4 seconds. So we make it smaller, bring it to 3, bring it to 2, bring it to 1, bring it to 0.1, okay, closer to 1 second, okay? So it becomes 1.01 and 1.0001, right? So as close as possible to 0. So these terms, okay, that is actually called the differentiation of the functions of x with regards to time. All right, so if we have exactly a functions of x, then we just need to differentiate it against with respect to time, then we will get immediately the instantaneous velocity at the time that we wanted. If we want at 2 seconds, we just substitute t as 2. If we want to find what is the instantaneous velocity at 5 seconds, we just substitute t as 5. Okay, all right. So from here, we will be able to determine exact velocity at that time. All right, so let us look at the example that what we have seen earlier. Just now we already looked at the example, right? From 1 second to the 4th second. Okay, the first second to the fourth second. So what we actually obtained just now is the average, as you can see, right? The average velocity is the red line, this straight line, the red line, correct? Okay, so now if we want to get the instantaneous velocity at 2 seconds, how do we do that? If we want to get the instantaneous velocity at 2 seconds, we just need to do this. We just need to move. Okay, we just need to move the time here. Initially, we said at 1 second. Okay, so we just move this time as close as possible to 2 seconds. Same thing from the 4th second, we also bring it as close as possible to 2 seconds, because that's what we want. We want to find what is the instantaneous velocity at 2 seconds. So this time difference here, okay, this is what we mean. This times difference, okay, we try to make it as small as possible. So that's why just now it is actually closest to 0. So if that is the case, then you can see the point here now, right? This point, okay, this point here. So we already have a point. Of course, not only a point. There are 2 points that we bring from the first and from the fourth. When we bring it too close, it looks like a point to us because the difference is only 0.0001 second. So for us, okay, a naked eye seems like 1 point. So we just need to draw the tangent line at 2 seconds. So this blue line, okay, this blue line is the tangent to the 2 seconds. So what do? We just need to find the gradient of this blue line. All right, then we will obtain the instantaneous velocity at 2 seconds. All right, same thing. If we want to find the velocity at 4 seconds, we just need to get the gradient at 4 seconds. How do we do that? Of course, the same thing. We just need to bring the time difference, okay, from 1 second to 4 seconds. All right, so we have again 2 points there. Then we just need to connect. Okay, so as we say, that is only a point, right, for us. So we just need to draw the tangent line, which is this orange line, tangent to that point at 4 seconds. And then to get the instantaneous velocity, we find the gradient. Okay, we find the gradient of this orange line. Then we will get the instantaneous velocity. So that is how we actually obtain by graphical method. Okay, by graphical method, that is how we obtain. But of course, if by calculation, we just need to know this function. Okay, if we know the functions of this x with time, then we just need to differentiate to find the instantaneous velocity as what we defined just now. Okay, so I hope now you understand how we can actually find the instantaneous velocity without losing the information at the exact moment. Okay, all right, we can actually using a graph find the gradient tangent to the lines, or we differentiate the function of x with time. Okay, all right, so I hope you already got it. Then now we are going to look at the graph. Okay, the shape, the type of graph. Then I hope when we see the graph, then we can actually understood what actually is happening. Okay, so let us look at the displacement time graph here. The displacement time graph. So let us look at one by one. So if we saw the first one, A, what does that mean here for A? Yeah? What does that mean?
The velocity of the object.
Constant velocity.
Yes. What we get here is v constant. All right. So just now we already say to get the velocity, we just need to get the gradient of the displacement time graph. All right. So The first one, we know that it is actually a constant velocity. Okay, a constant velocity here. Okay, right? How about the second diagram? How can we say about V1 and V2? Between V1 and V2.
V1 is greater than V2.
Yes, of course. All right. V1, the gradient is bigger. So it means the value of the velocity of V1 is bigger than V2. All right. Very good. And then how about the third one? What does it mean?
Object not moving, stationary.
So what can we say about velocity?
Zero velocity. So zero.
Yeah, when it's stationary, it means the velocity is 0. All right. So that is very clear. All right. The velocity is 0. And then how about the, oh, okay, it's not out. Okay, the velocity is 0. Okay. Then how about the fourth one? How can we say about this graph? It going up, suddenly coming down.
Object move in positive direction with constant velocity until t, then change into negative direction with constant velocity.
That's right. Very clear. Good. Very clear explanation. Okay. Very clear. Okay. So we can see that initially this object actually moved in the positive directions, and it suddenly, when it is reached the time t, it actually changed its direction. Okay. It changed its directions to the negative directions. Okay. So it abruptly changed its directions at the time t. Okay, all right. So that is the fourth one. How about the last one? What does it mean?
Decreasing velocity, super fast.
Okay, very good. So as just now we say, if we find the gradient at any point, right, then we will obtain the velocity. So if we can actually find at every tangent, you can see that the tangent actually is decreasing and decreasing. Right now, it's actually going to horizontal. So what we can say is the velocity is actually slowly decreasing. All right. So the velocity is actually decreasing slowly and slowly. Okay. All right. Good. Okay. So I hope you all understand this very clearly. The displacement time graph, how does it change? Then what does means to us? Okay, what does it mean to us? You have to be very clear. Okay, so let us have a short break. Okay, the time is already almost 5:30. So let us have a short break, 5 minutes. Is it all right?
Okay, sir. Yeah, okay, sir.
Okay, good. Let's have a short break before we continue to the next part. Okay.
Okay, thank you, sir.
Yeah.
Okay, thanks.
Thank you, sir.
Yeah, yeah. We look at the next part later. Okay. Okay, so seems this topic is still very simple, right? Can we start now? Is it enough break for 3 minutes?
Yes, sir.
Can ya? Okay, good. So let us continue. All right, let us continue. Of course, I hope everyone is already back. Okay, so let us look at the next one. Okay, so we just arrived or complete the velocity definition. Now we are going to look at the acceleration. So when the velocity change, okay, just now we are just looking at the constant velocity, and then the velocity not really changed by the force. Okay, so the object move with very constant motions. Now if something disturbed, okay, of course we are going to learn that in the next lesson. Okay, then we will obtain the acceleration. Okay, we will obtain the acceleration. So again, the acceleration is a vector quantity, so it is defined as the change of velocity over the time. Okay, so this is the change of velocity, all right, and then over the time interval, all right, over the time interval. So that is the average. As you can see, it is the total change here. We are looking at the final minus the initial, right? So the average acceleration, again, we will lose the informations, all right? We will lose the information. Why we say so? Let us look at this instantaneous. This is what I mean, all right? This is what I mean. If we are looking at the motions, okay, we are looking at the motions just now, right? So if we are taking this time interval with the velocity, okay, right? So if the object actually moves from one velocity to another velocity, something like this, okay, all right? So the object actually taking the path, okay, object is taking the path, something like this, okay, from V1 to V2. Okay, right. So this is the functions of the velocity. This is the actual functions of velocity with time. All right. So this is the actual motions of the velocity. All right. This is the actual motions of the velocity. But when we take the average, okay, so this is the average. Okay, this is the average acceleration. All right. So we have, sorry. Why the writing? Okay, so this is the average. Okay, all right. So this is the average. So we actually lost out all the informations that is actually takes place here. All right, during this time interval. Okay, during this time interval here. Okay, so this is the time interval that we consider. Right, between V1 to V2. All right, okay. So therefore, if we want to make sure we don't lose any information on the acceleration, we try to make the time difference closest possible to zero. So if we want to find out what is the acceleration actually at this time t, so we bring the time from here closest possible to t to make sure the time difference here closest possible to zero. All right, then again we obtain the function of differentiation with respect to time. So we can just differentiate the functions of v with respect to t, then we obtain the accelerations at that particular instant. All right, so that is how we actually obtain, right, for the instantaneous acceleration. Okay, instantaneous acceleration. Okay, so let us look at the example. Okay, so let us look at the example. Of course, we look at the average first. Okay, so we have this example for vehicles accelerate along straight line. Okay, so it actually starts from rest. Okay, start from rest and then goes with a speed of 75 kilometers per hour. Okay, right, 75 kilometer per hour to the right, as like this diagram here. Okay, so in 5 seconds. So what is the magnitude of its average acceleration? Okay, so it says it accelerate. Okay, it's accelerate. So of course, when it accelerate, we want to find acceleration, then we know exactly there must be in certain specific direction. So we just assume it towards the right. Then we have this information. Okay, 75 kilometers per hour is the final. It takes 5 seconds to reach that. Okay, so how do we do this? What is the first step? What should we do? Yeah? Anyone?
Find the acceleration.
Sorry?
Find the acceleration using the v minus u over t.
Okay, so can we calculate immediately?
Determine the initial, final, and time interval first, as well as the initial and final velocity.
Again? Find what?
Determine initial velocity, final velocity, and time interval.
Oh,
We
okay.
need to change
Write down.
the 75 kilometer per hour to meter per second.
Yeah, that's right. Okay. Yes, just like your friends mentioned. Okay. So we need to determine what is the initial, what is the final, and what is the time. And of course, the most important, the one that our friends finally mentioned, is to actually make sure the units. Okay, the units. So here they gave us 75 kilometers per hour. So we need to actually find in meters per second. So that is our first step. Okay, that is our first step. Of course, if we want to place it in one equation, is slightly lengthy. Okay, but of course, it's the best is for us to show first. Okay, the conversion, right? The conversion of kilometers per hour to meters per second. Okay, so we can give the answer in a fraction like this, or if you want to give a decimal, also fine. But since it's still not the final answer, so normally I like to actually put it in a fraction form. All right. Okay, so at least it's not that crowded already if we want to show together with the calculation, right? Okay, then only we write the acceleration. Okay, so we know exactly already it is starting from rest, so the initials is 0. Okay, the initial is 0. Okay, good. All right, 5 seconds. So we just substitute the value that we obtain. Okay, 125 over 6 minus 0 over 5. So we obtain it is actually equivalent to 4.17 meter per second squared. Okay, so from this answer, of course, before we find the answer, we already know there must be a positive acceleration, which means acceleration. It's not deceleration. Okay, so when we have a positive, we know it is acceleration, so is correct. Okay, right, it's correct. Okay, very good. Then next we look at the second example. Okay, the second example, it is having a car moving along the highway. Okay, so we were asked to choose the positive direction, that's the X, okay, for this particular car motion. But suddenly the driver puts a brakes, okay, then the speed of course will slow down, okay, because it brakes. So the initial is 15 and then it slows down to 5 meters per second in 5 seconds. So what is the average accelerations now? Okay, so how do we do this? Can we start it immediately?
Yes, we can.
Yes.
Yeah, good. Very good. Yeah, everything is fine for us. The unit, everything. All right. So we can start immediately. Okay, to find what is the average acceleration. So our average acceleration is equivalent to -2 meter per second per second. So here we know exactly our answer must be in negative because it decelerates. Okay, all right, good. So we have -2. It means that is the correct one. Okay, all right, we have -2 meter per second per second. Okay, so I hope everyone already familiar with these average things and so on. Okay, how to calculate from the definition. Then now we want to look at the graph again. Okay, so just now we look at the graph of displacement with time. Now we want to look at the graph of velocity with time. Okay, so we want to know the meaning as well for each of the graph. Then only we will be able to immediately solve any particular graphical motion. Okay, so for the first one, what does it mean?
It's accelerating.
Again?
Constant acceleration.
Accelerating.
Yes, the first one, it says accelerating, of course, but it is constant. Okay, we must mention that as well. A is constant. All right, A is constant. And then how about the second one?
A1 greater than A2.
Greater than A2. Oh.
Yes, it's also very obvious. Accelerations of A1 is much larger than A2. And how about the third one?
Zero acceleration.
Zero acceleration.
How about motion? Is it stationary?
Moving with
Moving.
velocity.
No.
Depends.
What do you mean depends?
It is moving at constant speed.
Yes.
Yeah, uniform velocity.
Yes, of course. You see, I asked a bit only. I want to see the confidence level. Okay, want to see the confidence level. So everyone seems good, confident. Okay, acceleration is 0. Although acceleration is 0, we must see whether the graph. Okay, is it stationary? No, it is not. The velocity here is not 0. Okay, the velocity is not 0. The velocity has some value here. Okay, so it is actually moving with certain velocity, which is constant velocity. Okay, that's why acceleration is 0. Okay, how about the fourth one? How about the fourth diagram? How about the fourth diagram?
Acceleration is negative.
Yes, the object is actually decelerating. Acceleration is negative, so object is slowing down. Okay, very good. How about the final one?
Decreasing acceleration.
Yes, it's also similar to the previous one. Okay, so we have, if the tangent of this curve, we try to find it at each point, then the accelerations is actually continuously slowing down. I mean, decreasing. Okay, the magnitude is smaller and smaller. Okay. All right, so we would like to have some conclusion or relations here between velocity and acceleration as well. How do we know whether they are actually accelerating and then moving in a positive direction or negative direction? Are they moving in which directions? Okay, so we have some conclusion, a short conclusion here between the velocity and accelerations here. Okay, so this is quite important summary for you all. Okay, right? Probably sometimes you are thinking whether it is true or not. Then we can just review back this relation. Okay, whether it's acceleration or deceleration. So we have, if they are the same sign, which means V is positive, A is positive, that means same sign, then this object is accelerating. If V is negative, A also negative, that means they also accelerating because V is moving in the negative direction, although A is negative, but V is moving in the negative direction. So it is actually accelerating as well. And then if it is opposite sign, one is positive, one is negative, then it's very clear that this object is decelerating. Okay, all right. So I hope you all able to conclude, okay, have this short conclusion with the relation of velocity and acceleration. Okay, understand? Can you understand? Any question? Can you?
No question, sir.
Okay, good, very good. Then we have one final graph questions that is also very famous. I'm sure everyone also know about this. Okay, the velocity time graph. What can we obtain from velocity time graph? Anyone?
Displacement.
Displacement.
And acceleration.
That's right. Okay, this is the important information as well. Okay, a velocity time graph, the area under velocity time graph allow us to know the displacement of the object. Okay, all right, good. Then, since everyone know already, okay, the secret of the area under the graph is the displacement. So, what is the first displacement for first one? First diagram, what is the displacement? Anyone? What is the first displacement?
Is it 300?
300 meter.
Yeah, 300 meter.
How do you get that?
20 times 15.
That's right. This first one is very easy, very direct. It's just a square, right? So the distance or the displacement, sorry, okay, the displacement, since it's velocity time graph, okay, so the displacement is 300 meters. How about the second displacement? Second graph.
25 meters.
25.
25. So same thing, okay, we find the area of the triangle, right? Okay, so we have 25 meters, okay, so that is the another important information for the velocity time graph. Okay, any question for velocity time graph?
No question, sir.
Okay, very good. Okay, very good. So we go to the last part. Okay, I believe we will be able to go to the next one. Okay, because sorry. Yeah.
Could you please go to, yes, why did we like say that displacement is v, not x? Why didn't we say x equals to velocity multiplied by time?
Displacement equals to velocity times time, yeah?
Yeah, why did we refer to displacement using the symbol v, not x? Isn't d for distance?
Oh, okay, okay. It's all right. Normally we use r for this displacement, yeah. But it's all right as long as you actually mention the displacement. Okay, you show the calculation. I don't mind. All right.
Understood. So, like, this is not something really important. Like whether we
not to say very. Yeah, not to say very, but of course it is good that you really follow. Okay, yeah, you really follow the reference every time. We normally take the displacement as r. Okay, we normally use displacement as r or x. All right. Okay, the distance sometimes we use d or sometimes we use s. Okay, right. So here, since the equations, I also just use d, then of course, thank you for the reminding, okay, right? So I hope you all, pay attention to this variable as well, okay, if you can, because later on, just like the next part, you also probably will be thinking, oh, why we not, sir? Why we can just use u, just like later, okay, the topic later, right? But of course here if we talk about displacement, normally we use r and x. All right. Okay. Thank you for the questions. Yeah. Yeah. Thanks.
Thank you, sir.
Okay. Welcome. Okay. Yeah, this is what I mean. Okay. So for this uniform accelerated motion. Okay. So all our motion. Okay. I would like to state here. Okay. Generally, all our motion, we are going to look at a motion with actually uniform acceleration. Okay. Our motion, generally, we are having a constant acceleration. All right. So when we say acceleration is constant, okay, when we say acceleration is constant, then we actually could equate these two terms, these two variables here, as you can see. Okay, why we say A equals to A bar, average. Okay, just now we say how we calculate average velocity, average acceleration. Okay, so we actually just now define average accelerations is defined as the final velocity minus the initial velocity over the time interval. Right or not? But this is average. Okay, this is average. But now, since the acceleration is constant or uniform, okay, all right, so we can see that this is the motion. Okay, when the acceleration is uniform, this is the graph for acceleration. A is constant. You can see that A is constant. If we look at the graph of velocity, okay, it's just a linear increment. Okay, it's a linear increment. It didn't have the curve, just like displacement. Of course, displacement will be a curve. Okay, but for velocity, it's a straight line. Okay, it's a straight increment. Okay, and the line, the graph for acceleration is the horizontal, a constant acceleration. So if we actually compare with the graph earlier, right? If we compare with the graph velocity and time earlier, right? We have this kind of motion for acceleration, right or not? So it is not linear, it is an increment. So if we get the tangent, right? If we get the tangent, every time the tangent is different slope. But if we try to get this graph here, the tangent at this point, at this time, if we draw a straight line, it's still a same straight line. If we draw the straight line here also, the gradient at this line also is still the red gradient here. It's still the same. Correct or not? So therefore, we can state that the average is just the same as the instantaneous acceleration. Therefore, we can use the definition of average here because average and instantaneous is the same already. So therefore, we can write now the accelerations is given by these equations as well. All right, therefore, we can also say the instantaneous accelerations now also can be written as V minus V naught over T. Okay, so V naught, of course, is the initial. Okay, sometimes you can write it as U if you like. Okay, this is just following the reference book. Okay, so if we arrange, okay, if we arrange these equations here, then we will obtain the our first special equation. Okay, the famous equation. V equals to V naught plus AT. All right, correct now. So V equals to U plus AT. That is the common equations that we have. Okay, all right. Then we can go to the average velocity. Okay, if we try to recall back how we define average velocity. So this is how we define average velocity, which is equals to the final displacement minus initial displacement divided by time. Okay, so this is how we define average velocity. So we arrange it. Okay, we name it as A. Okay, so we have x minus the initial. Sometimes, most of the time, not sometimes, most of the time we take initial as the origin. That means x naught is 0 at the origin, but it's still important to write here. Sometimes if it is not started from the origin, so we need to have this initial position. Okay, fine. So that's how we have the first relations for average velocity. Okay, then if you look at this diagram here, this second diagram here, we also can obtain the average velocity from this diagram, right or not? Okay, so if we take from this initial until this time, okay, until this point here, then we will also obtain the average velocity, correct or not? Okay, so we obtain is equals to half, okay, we obtain equals to half V naught plus V. It means that, okay, it means if we actually consider this line, okay, just now we already draw this, okay, at this time, okay. So if we consider this is the initial and then this is the final that we considered, okay, so this is V, and we want to find what is the average velocity between these 2 points, these 2 times, these 2 duration. Then we just need to add up V naught with V, and then we divide by 2, then we get the average. So this is the average velocity. Okay, this is the average velocity. This is only valid, remember, this is only valid when we have constant acceleration. Okay, when it is uniform acceleration. Okay, then this, so we have the first equation just now from the definitions here, A, right? Then we also obtain the second equations, right, from the diagram, okay, from the diagram for the average velocity with constant acceleration, all right? Then we have these 2 equations together, we substitute this, okay, V into A, all right, into these terms here, V average, all right, then we will obtain the second equations, okay, so x minus x naught equals to half V naught plus V times T, right or not? So we look at here. So this x naught, we bring it to the left side. So that's why it becomes x minus x naught. And then V average here is half V naught plus V, and then times with T. So we obtain the second equations. All right. Okay. And then for the third equation, we just need to substitute the first equations just now into the second equation. We have already, the first equations is in terms of V already, right or not? So we substitute into the second equations here, okay, V. Okay, we substitute V, then we will obtain these equations here, the third equations. How we obtain that? Okay, let us see. If we have x minus x naught, okay, x minus x naught equals to half, okay, V naught plus, so V equals to V naught plus AT. Okay, times with T. All right, so we simplify this. Okay, so you get 2V naught Okay, we multiply with half outside. That's why we obtain this V naught T. Okay, and then half AT squared. That's how we get half AT squared. That's how we got the third equation. All right, that's how we got the third equation. Okay, all right. So I want you to go back and try how you actually obtain this fourth and fifth equations. Okay, all right. I believe you all can try this at home. Okay, how you want to obtain that is already mentioned to you. Okay, replacing t into 2, and then the fourth, then the fifth one is replacing v naught into 2. Okay, so you try this and we discuss in the next lesson. Okay, all right. Thank you very much. So I hope you all understood this lesson very well. Okay, thank you and have a nice day.
Thank you, sir. Have a nice day too. Bye-bye.
Okay, bye-bye.
Thank you, sir. Stay safe.
Bye, sir.
Okay, take care. Have a
Thank you,
nice
sir.
day.
Thank you, sir.
Okay, thank you.